Hi, today we are going to look at the velocity time graphs for constant acceleration motion. So imagine you have a slope over here and you have a ball right at the top of the slope and it starts at rest. So at t equals 0, the velocity of the ball at rest should naturally be 0. Now, as you would have guessed, gravity pulls the ball down. So after say 1 second, you might see the ball somewhere over here. Alright, with a velocity downwards along the slope. In another second, t equals to 2, you might see the ball move faster and faster and faster. So you might probably find it somewhere around here. Then the next second, at t equals to 3, the ball should probably be at its fastest over here. Now, say the acceleration of the ball along the slope is 3 meters per second squared. And if you recall, the definition of acceleration is the rate of change of velocity. So it tells you with every passing second, how much does the velocity increase. Therefore, if the velocity increases by 3 meters per second every second, at 1 second, the velocity will be 3 meters per second. At the second, the velocity will therefore increase by 3 again to become 6. And at the third second, the velocity will increase by another 3 to become 9 meters per second. Let's take a look at how this data will look on a VT graph, or velocity time graph. So at t equals 0, the velocity is at 0. At t equals to 1, velocity is at 3. At t equals to 2, velocity is at 6. At t equals to 3 seconds, velocity is at 9. And if you connect, or rather if you draw a best fit line, you should have a straight velocity time graph. This velocity time graph tells you about the velocity of the object undergoing constant acceleration motion downwards along the slope. Now, there is one more thing about a VT graph that you need to know. That is how to find acceleration. The acceleration of the object can be easily gotten from a VT graph by finding the gradient of the graph. So as you would have learned in mathematics, the gradient of a straight line graph is simply rise over run. So I will take two coordinates. Say I will take this coordinate of 3, 9, and say this coordinate of 1, 3 to find the gradient. That will be 9 minus 3 divided by 3 minus 1, which will therefore get you 3 meters per second squared. As you can see, this way of finding acceleration from a VT graph tallies with the actual acceleration of the object. Now, let's move on to a second scenario. Imagine now you have a slope, the same slope, and you have the object right at the start of the slope, at the bottom of the slope, and you decided to push the object up with, say, an initial velocity of negative 9 meters per second. Now, bear in mind, because you let downwards to be positive, therefore going up the slope will give you a negative velocity vector. Now, in the next second, with an acceleration of the same acceleration of 3 meters per second squared. Let's start with the table first. In the first second, your velocity will increase by 3 meters per second squared. Sorry, will increase by 3 meters per second. So, negative 9, if I add a 3, increase by 3, I'll get negative 6. In the next second, I do the same thing. I increase the velocity by 3 meters per second, I will get negative 3. And I increase the velocity by another 3 meters per second, I'll get 0. And this table now shows you the velocity time data of the object. Back to this diagram, in the first second, you probably see the object still moving very fast because you shoot the object up the slope at a very high speed, very fast speed. So you probably find the object somewhere here at t equals to 1, still moving up. But as the object moves up, naturally it will slow down. So t equals to 2, you probably find it somewhere here, starting to slow down. And at t equals to 3, perhaps it will stop just here. Alright? So, same thing, if I start to plot this data onto a VT graph, I will get 0, -9 over here, 1, -6 over here, 2, -3 over here, 3 and 0 over here. And you can again see, because the object is moving with a constant acceleration, the VT graph is again a straight line graph. And you can again repeat the whole process of finding gradient by using the same formula, rise over run. And say if I choose any two coordinates, I choose say this coordinate 3, 0, and a random coordinate here, say 1, -6. Doing rise over run will get me 0 minus -6. Be careful of the double negatives. 3 minus away 1, and if you solve this, you will again get 3 meter per second squared. So before I end off the video, I will want you to think about how would you draw a VT graph for this scenario. For the scenario of an object being shot up a slope, it started from here, it's being shot up the slope, it slows down, it stops at the peak, and then it starts to come back down to the bottom.